looking at polynomials and rational inequalities. And so first, let's look at the graph in front of us and let's answer the questions. So looking at the graph, we're trying to find when f of x is less than 0. F of x is just representing my y value of the graph. And so if I'm looking at when my y value is less than 0, those are values where my graph falls below the x-axis. And so I'm just going to outline where it falls below the x-axis. But when we write these values, we're writing these values either as an inequality using x or as an interval notation. In this class, we've been using interval notation a lot. So our graph f of x is less than 0 for these x values. And so it starts at the x value of -1, but doesn't include. So we put the parentheses there instead of the bracket. So I have -1 comma, and then I go to the x value of 1. It's not including because the value 1 makes it equal 0. So again, we're going to put a parentheses here. Union, because it has the values here from x from -1 to 1, not including, and we're using the values anything bigger than 2. That will always be below the x-axis. And so this is from 2 to infinity. So I think some of you in that last exam had some problems with the interval notation, and you would want to start with a y value or a point. So there was some confusion there. So make sure that you have that down. And if you have any questions, let me know. So part B, we want f of x greater than or equal to 0. And so because it equals 0, we want to look at the x-intercepts, the points on the x-axis, and we're going to include those. We're looking for our y values that are greater than or equal to 0. So these are values that are above the x-axis or touching the x-axis. And so let's locate those. And so above the x-axis would be here and here. And so we're looking at all the x values from -infinity until we hit -1. So those are x values that would give us a y value bigger than or equal to 0. So -infinity to -1. Union, and then all the x values between and including 1 and 2. So the next example that we have is a rational, would be a graph of a rational inequality. And before we answer A and B, you guys should be able to look at this and tell me what the asymptotes are. So if we were looking in the end behaviors of our graph, and so we use this LIM, represents the limit. Where is our y value going on our function as we approach some value? So if we were approaching -infinity of our graph f of x, what y value is this graph heading towards, if any? Or is it going to positive or negative infinity? We'll notice here as our graph is going to -infinity, this is hugging, it's going to start hugging this line y equals 1. And so that graph is getting closer and closer to y equals 1 as x goes to -infinity. So this would be 1. Same sort of idea when we look at the end behaviors as x goes to positive infinity. This y value is getting closer and closer to the y value of 1. And so our end behaviors are going to 1, and we have a horizontal asymptote at y equals 1. Okay, vertical asymptotes, that's where we were getting closer and closer to a single x value. And as we get closer and closer to that X value on the left and the X value on the right, the graph is either shooting up to positive infinity or shooting down to negative infinity, or it could be opposite on each side of that X value. In this case, it's not. But if you look at X equals -1 here, as we look at the limit, oops, as X approached -1, so it could be, like I said, could be approaching different positive or negative infinity, depending on for a vertical asymptote. So to represent this, and I didn't really mean to get into so much of this detail, but to represent this on the left of that value of the X that we're approaching, let's put a negative. You put a negative like a superscript, or kind of what looks like an exponent, but not. Put a negative on there, and that says we're coming in when X is less than -1. So as we're coming into this X value less than -1 on the left-hand side of this asymptote, we're shooting off to positive infinity. Same idea as we're looking as X approaching -1, but this time from the right-hand side. And so to denote that I'm coming in on the right-hand side of that X value, I'm going to put a superscript of a plus sign. So coming in on the right of -1 of f of X, our graph also goes up to positive infinity. So I just kind of wanted to review asymptotes with you, because I know it's been a couple weeks. So let's look at the graph here, and let's look at finding f of X where it's greater than 0. So those are all Y values that are greater than 0 on this graph. We're trying to find the X values that give us those Y values. And so I see that my graph, and I'm going to just look at the X values, my graph is above the X axis, coming in from negative infinity until I hit this X intercept. And then it dips below the X axis. So I'm coming in from negative infinity, negative infinity to +1, strictly greater. So parentheses. And then the next X intercept is 3. And so I see that it's above the X axis when X is greater than 3. So union 3 to infinity. The only time this graph goes below the X axis is this interval between 1 and 3. Okay, this is where we have to be careful. Recall that your vertical asymptotes occurred on values of X which were undefined, values which set our denominator equals 0, but not also our numerator. And so we have an asymptote here. We're never going to have that X value. And so we do need to denote that when we're looking at this. So it's less than or equal to 0. So I can include my X intercept. So I'm going to include my 1. But then I need to stop here. I can't have X equals negative or X equals 2. So I'm going to stop there at 2. Can't include it because it's undefined there. Union, and then 2, not including, and I can include 3 because that makes it equal 0. And that's a true statement. So you should be able to look at a graph and be able to find when f of X is less than 0 or greater than 0, or those inequalities with the equal sign. You should also be able to go through and graph things like we've been graphing earlier in this section, and then be able to then find where it's greater than or equal to 0 or less than or equal to 0. and then solve it algebraically, which we'll talk about in a minute. Okay. So let me see if there's questions before we move on to this example. So the next example says, so R of X is solve R of X, which is less than 0, where R of X is equal to, or we just have X in our numerator, and then that's all over the two parentheses, one with X minus 1 inside, and the other parentheses with X plus 2 inside. So first thing that we're going to do is we're going to graph these, or graph R of X. And so I see that this is a rational function. And so I'm going to first locate my vertical asymptotes. So recall vertical asymptotes occur which set our denominator equal to 0, but not also our numerator. And so it's already factored for us, but if it wasn't factored, I would factor both my numerator and denominator. And so we're looking at when is X minus 1 equal to 0? Well, that's when X is 1. So X equals 1, and that doesn't set my numerator equal to 0. So it's a vertical asymptote. And then when is X plus 2 equal to 0? Because we need to exclude it from our domain. And so X cannot be negative 2. Negative 2 doesn't set my numerator equal to 0. So X equals negative 2 is also a vertical asymptote. Looking at horizontal asymptote, remember horizontal asymptotes occurred on values which, well, actually, it depend on the degree of the numerator and the degree of the denominator. And so it depends on if the degree of the numerator or denominator was larger, or if they were the same. And there was 3 different case scenarios. And if the degree of the denominator is larger, it goes off to y equals 0, the x-axis. You're going to have a horizontal asymptote at y equals 0. And if I distribute out my denominator, I'd get an x squared. My degree is 2. My degree of my numerator is 1, so that's smaller. So I have a horizontal asymptote on my x-axis, which is the line y equals 0. So let's graph what we have so far, and then we're going to find our intercepts and maybe a couple other points if we need them to see what the graph of R of X looks like. So my x-axis is this horizontal asymptote. I know I have a vertical asymptote at 1 and negative 2. So let's put our vertical lines there, dotted. Okay, now if we look at what is R of 0, when X is 0, that would be our y-intercept, but it ends up that we got 0 over negative 1 times 2, which is negative 2, which is equal to 0. So our graph is either just touching or crossing the x-intercept at the origin 0, 0. Look at the multiplicity. This will actually help us if the graph is going to just touch it and turn around, or if it's going to cross it. If I was looking at just X here, my multiplicity is 1. If it was an odd multiplicity, it crossed. So now let's see, is it going to fall above or below the x-axis when X is between negative 2 and 0? So just choose some value. So let's say that we choose negative 1. So if we plug in negative 1 wherever we see an X in R of X, we would get back negative 1 all over negative 1 minus 1. So that's a negative 2. All times negative 1 plus 2, which is 1. So this gives me back positive 1/2. So when X equals negative 1, I'm above the x-axis. So right there, I know what's happening as X is approaching negative 2 on the right-hand side. Because of where the asymptote is, there's no other x-intercepts. And so it's going to look like this. Again, I said it's going to cross it because of the multiplicity. And so it's going to have to hug the x vertical asymptote like that between 0 and 1. So now all we have to do is look at what's happening on the left-hand side of -2 and what's happening on the right-hand side of 1. We know the end behaviors are going to be hugging the x-axis because of the horizontal asymptote. So we just need to test one number to see if we're above or below the x-axis when we're x is less than -2. So let's say we plug in -3. So if we do that, we get -3 in our numerator all over -3 minus 1, so -4 times -3 plus 2, so that's -1. This gives me -3/4. This is below the x-axis. And knowing that then as x is approaching -2 on the left-hand side, this is shooting down to -infinity. And as x is approaching -infinity, my graph is going to be hugging this y-axis, x-axis, y equals 0. Same idea, choose a point bigger than 1. So let's choose 2. If we plug in 2 wherever we see an x, we would get 2 all over 2 minus 1, which is 1. And then 2 plus 2, which is 4. So this is going to give me positive 1/2. So it's above the x-axis. So I know as x is approaching 1 on the right-hand side, this is going to be shooting off to positive infinity. And as x is going to positive infinity, our graph is hugging the line y equals 0. Okay, so that was a great kind of review of graphing rational functions, but now we can use this to answer our question. And so we're trying to find when is r of x less than 0? When is our graph falling below the y-axis, x-axis? And so looking at this, r of x is less than 0. Well, I'm getting all the values, right, coming in from -infinity until I hit this vertical asymptote. So this is -infinity to -2, then union. Now notice that it's below the x-axis, starting at x equals 0. It's hitting the origin, but then after that, and between 1, it's below the x-axis. And so we now have union 0 to 1, not including either of them. Now we're going to look at solving these algebraically, which can be a lot faster than graphing. Notice that back here, when we were graphing this function, we had to look at values where our intercepts were, because that's where it could change from above or below the x-axis. And we also had to look at where our asymptotes are. And so when we're graphing polynomial or rational inequalities algebraically, you want to follow the following steps. So you're going to write your inequality. So the polynomial or rational function f is on the left-hand side and the 0 is on the right-hand side in one of the following forms. So f of x is greater than 0, f of x is greater than or equal to 0, f of x is less than 0, or f of x is less than or equal to 0. For rational functions, be sure that the left-hand side is written as a single quotient and find the domain. So that's key here, that it's a single quotient. So a lot of times students, when it's a rational inequality, want to clear the fractions. And we don't want to clear the fraction because that is going to clear where it's crossing, not crossing, where we have a vertical asymptote. So make sure that you don't clear your fractions for inequalities if it's if it's just a number, you can, but if there's variables down there, you cannot. And rewrite it as a single fraction. Okay, step 2, determine the real numbers at which f of x equals 0. And if the function is rational, the real numbers at which the function is undefined. Okay, values which set our denominator equals 0. Use numbers found in step 2 to subdivide the real number line into intervals, and then select a number on each side of our interval and evaluate f at the number. Okay, so we're going to test numbers, and we did this for quadratic inequalities when we're solving these. And if you took Math 52, this was covered in that class too. So if the value of f is positive, then f of x is greater than 0 for all numbers of x in that interval. If the value of f is negative when we plug in a test point, then our y value is less than 0 for all of the number x values in that interval. And if we have the inequality is not strict, like less than or equal to or greater than or equal to, then we want to include the values which set our denominator, which set our function f of x equal to 0 that are in our domain of f in the solution set. So we're going to be careful. We need to exclude values if we have the greater than or equal to or less than or equal to values which give us vertical asymptotes. So be careful to exclude values of x where it's undefined. So let's look at an example of this. So this example, we have the inequality x to the 4th is less than 9x squared. And it tells us to solve each inequality algebraically. So we want to get everything to one side of the inequality. So we would subtract 9x squared on both sides. Those are not like terms, so I'm going to rewrite it as x squared minus 9x squared is less than 0. We now want to factor this so we can find out when this is equal to 0. I noticed that we have an x squared in common, so we can pull that out. And we would get x squared minus 9 is less than 0. We have a difference of squares, so we can factor that. So we have x squared minus, so we have x squared, and then we have times x minus 3, all times x plus 3. This is less than 0. So our values, what set this equal to 0? I call those our critical numbers. And these are when x squared equals to 0, so that's x equals 0. When x minus 3 equals 0, so x is 3. And when x plus 3 equals 0, so when x is negative 3. So we're putting those values on our number line. So because of those being 3 values that set it equal to 0, I'm going to have 1, 2, 3, 4 intervals that I'm going to have to test to see if it's going to be above or below the x-axis. So choose something that is less than negative 3. You can never choose that value that you found, that critical value. So let's look at x equals negative 4. We want to plug it in to see if this is a true statement or not. And so really all we care about is, do we have a positive number or do we have a negative number back? And so let's just think about it with this factored form. If I take negative 4 and we square that quantity, well, negative 4 times negative 4 is positive 16. So that's a positive number. If we plug in negative 4 for x here, so we have x minus 3, and plugging in negative 4, that's going to make it a negative number. And then plugging in negative 4 into the second parentheses, we got negative 4 plus 3, which is negative 1, which is negative. And we're asking ourselves, is this value less than 0? and that's going to be a false statement. The value that we get is positive. So that tells me that the graph is above the x-axis there. So now choose something between -3 and 0. So how about x equals -1? And if we plug in -1 here, square that quantity, we have a positive number. Plug in -1 here, -3, we have a negative number. And plug in -1 plus 3, that's positive. And we're looking to see, is that number less than 0? Positive times a negative is a negative, and a negative times a positive is a negative. So we have a negative number, which that means it is true. It's less than 0. Choose a number between 0 and 3. So if we chose x equals 1, 1 squared is positive, 1 minus 3 is negative, 1 plus 3 is positive. And we want to know, is this less than 0? It's a negative number, and a negative number is less than 0, so this is true. X equals a number bigger than 3. So how about x equals 4? Well, 4 squared is positive, 4 minus 3 is positive, and 4 plus 3 is positive. So multiplying all positive numbers together, there's no way to get that less than 0. And so this is false. So to find out where x the fourth is less than 9x squared, we have the following values. Our solution is not including because it's strictly less than. So parentheses -3, comma 0, parentheses union, parentheses 0 to 3 parentheses. And this is how we can write it in inequality notation. I don't like my or. Okay, it doesn't matter though. Write it that way. So we'll look at one more example from this section, and then we'll take a break, come back, and jump into the next section. So one more example, let's look at one which is a rational inequality. So our next inequality is 5 all over x minus 3. This is greater than 3 all over x plus 1. So again, we want to get everything to one side of the inequality. So let's subtract 3 all over x plus 1 to both sides. And so we get 5 all over x minus 3 minus 3 all over x plus 1. This is greater than 0.
Oh my progress.
So we are going to rewrite this as a single fraction. And so we need a least common denominator. And our least common denominator is x minus 3 all times x plus 1. So in order to get a common denominator for the first fraction, I'm going to need to multiply this by x plus 1 all over x plus 1. Again, I cannot clear the fractions here. To get the common denominator for 3 over x plus 1, we're going to multiply that by a fancy one, and that fancy one is going to be x minus 3 all over x minus 3. So let's distribute in our numerator. We have 5 times the quantity x plus 1, and so that gives us back 5x plus 5. And then let's distribute. We have a minus here. So we're distributing -3 to both terms. So -3 times x is -3x, and -3 times -3 gives us +9, all over x plus 1, all times x minus 3, which is greater than 0. 5x minus 3x is 2x. 5 plus 9 is plus 14, all over x plus 1, x minus 3. We can factor out a 2 if we wanted to from the numerator. It doesn't really matter, but I'm going to do it anyway. So factoring out a 2 in the numerator, we have 2 all times the quantity x plus 7 all over x plus 1 and times x minus 3. So for our domain, x cannot set those denominator equal to 0. So x cannot be -1 and x cannot equal 3. Graphically, because these values don't set my numerator equal 0, we would be having a vertical asymptote at those values, x equals -1 and x equals 3. Those are part of our critical numbers. And then what sets it equal to 0? So what sets it equal to 0 is when our numerator is 0, and our numerator equals 0 at x equals -7. So our critical numbers that we're going to place on the number line are -7, -1, and 3. So again, we have 3 separate intervals. This is not to scale. And so we have 4 different places that we have to test. Again, we're really just worried, is this positive or negative? We don't really need to know what the number is. And so let's look at a number less than -7. So x, how about, is a -8. So going in here and plugging in -8 plus 7, that's going to make that a -1 times 2 is negative in the numerator.
I want to.
Chrisma, if you have a question, let me know. I just muted you. And this is all over. So -8 plus 1 is negative, all times -8 minus 3, which is negative. Is this greater than 0? No, because a negative divided by a positive is less than 0. So this is false. Okay. And this was negative, it's less than. Choose another number in between -7 and -1. So let's look at x equals -2. So plugging in -2 in the numerator, -2 plus 7, that's positive. All over -2 plus 1, that's negative. And -2 minus 3, that's negative. So my denominator, negative times negative, is positive. And so positive over positive is true. It's greater than 0. Choose anything between -1 and 3. If x is equals 0 is in that interval, that's always usually the easiest one to check. And so 0, wherever I see an x, well, 0 plus 7 positive times 2 is positive, 0 plus 1 is positive, and 0 minus 3 is negative. So I can see this is not greater than or equal to 0. This is false. This is below the x-axis. One more value, x equals 4, because that's bigger than 3. So x equals 4. 4 plus 7 is positive, times 2 is positive, all over 4 plus 1 is positive, and 4 minus 3 is positive, which is 1. So that would be greater than 0. So our solution, which I did not mean to do that, our solution is everything above the x-axis. And so our solution is going to be not including -7 to -1 and union parentheses 3 to infinity. So that is graphing, or that is solving rational inequalities and polynomial inequalities. So it's definitely different than solving just linear inequalities where we just isolated the x to one side, constants on the other side. You can either solve it graphically or you can solve it algebraically. I didn't want to do that.